strain energy density. Well, what is strain? Well, if you're given a particular object and you see that it is under certain deformable forces F1, F2 and F3, then it is bound to undergo some deformations. Then strain is defined as the change in the dimension because of those deformable forces divided by the original dimension. Well, the next term in this particular topic is energy. Well, energy is the capacity to work. Well, these particular definitions may seem as if they are just like childish, but these childish definitions have great implications and explanation. Well, let us look what they mean. This particular diagram shows the stress-strain diagram for any particular object. Well, to keep in mind, just remember that this particular axis denotes the stress. You also need to keep in mind that this particular symbol is called sigma and it means the stress. If you look at this particular axis denotes an E looking character. This is called epsilon, and well, it means the strain. This corresponds to the strain. This particular curve is the stress-strain diagram, the stress-strain curve for a particular object. This particular point, the last point which you can see in the curve, is called the rupture point, well, which corresponds to a point where the object breaks. I'm not going into detail of these all points, but let us see what this particular shaded area tells us. Well, this particular point corresponds to a stress which is known as the proportional limit. Well, I'm not going to define what a proportional limit means. Well, if I am applying a certain amount of deformable forces and if the internal resistive forces or the stress is under proportional limit, then this particular shaded area will give me the strain energy density. Just remember that this particular curve under proportional limit will give us the strain energy density. The proving has been given in the later videos. Well, now coming to this particular diagram, which looks a bit clumsy, you can see that this particular diagram, this particular curve is a replica of the previous curve, right? But they have been divided into certain parts. Well, of course they have some meaning. We'll look forward to what they mean. But over here you see that we are working on this particular point which corresponds to this particular point in this particular graph. Okay. Well, this point no longer corresponds to the proportional limit. This particular point corresponds to a point which is beyond the proportional limit. The proportional limit had to be somewhere over here. Well, in this particular diagram, what I try to show you that if I have a particular object under deformable forces, and if I apply forces to such an extent that the object starts to deform into a plastic nature deformation, okay, and I keep on increasing the stress till it comes to this particular point. This particular point, keep in mind, does not denote the rupture point. The rupture point, if you see, came a bit more down. Over here I have limited to this. This is not the rupture point. If it had to be the rupture point, then the rupture point would have come somewhere down here. Well, this will be explained in also the later videos. Now, if from here I start removing the load, or if I start removing the external forces, then the internal forces will also reduce in the similar manner. It will follow this particular curve. Amazing, this does not follow this particular curve. This particular thing follows this particular curve. Just remember, this particular line will be parallel to this particular line. So we have a different proportional limit. You can just see that because of increasing the particular stress and moving it into the plastic nature, we have increased the proportional limit till here, which was initially over here. We have increased it till here. That is not the discussion for this particular video. Now what you see is that as you keep on decreasing the the load, the stress decreases and decreases and decreases and decreases and comes to 0. Okay, now if you see in this particular graph, this particular region corresponded to the strain energy, the energy stored due to the deformation. Okay, well, it's very obvious. If you take a sponge and if you just squeeze it, you'll see that its shape has changed. The shape has changed just because you have applied some force. Now if you just remove that stress, if you just open your hand, you'll see that the sponge regains its shape. So you can just think it in the similar fashion, that if you have just removed, if you have some amount of stress in the proportional limit, then the amount of deformation would correspond to the strain energy density, or the energy stored because of the deformation. Now coming over here, well, as we saw in the previous graph, you can, if you correlate it, you would say that this particular whole region, or the area under this particular region, the whole region corresponds to the energy density, the strain energy density. But well, it is not so. Well, the basic definitions of energy, as I said, would come into play in this particular part. Well, now if you see, just look and appreciate the beauty of this particular concept, that as I decrease the load, the stress decreases, and if you see that when the stress is 0, or when the load is 0, still I have some amount of deformation, which has been because of the plastic nature of the deformation, because I had increased the load beyond the proportional limit. Now if you see this particular region, this particular triangle, only this particular triangle has been regained from this particular whole area. We have been able to regain, or you can say that we have been able to remove. When we come to this particular point, we have been able to just get back the energy stored in this particular region only. Why? Because only this particular deformation has been regained into its original shape, but we have been left with this amount of deformation. Well, you can argue that if there is some amount of deformation, then there must be some amount of internal energy still stored because of deformation. Well, now the beautiful concept of the definition of energy comes into play. As I said, that energy is the capacity to do work. If you have energy, you can do work. Now just think that I have removed all the loads. That means at this particular point, if it had some amount of energy because of the deformation, it should have done some work. But it doesn't do any work. And at this particular point, just imagine a rubber band. Okay, let this be a rubber band. Now if you apply a force over here and here, right, it just elongates and elongates. Keep on applying the forces, it just elongates and elongates. And if you just leave it, if this was its original length, now it would be this much. The original length would become this much. So this is what I'm corresponding over here. Now since its length has increased, that means there is some amount of deformation still left, when that deformation does not correspond to any storage of energy, because that particular energy, now you would just argue that if deformation, okay, corresponds to energy storage, and if I'm saying that at this particular point, when there is no load, there is some deformation. That means there should be some energy storage. Well, but from the definition of energy, it had to have some capacity to do work. Well, it has no capacity to do work, so we can say one thing, that the deformation over here that it has does not have any energy stored. So the question is, where does that energy go? Well, the energy is released in the form of heat or some other form. It is just released. So you can just say that the energy is not stored. Well, it's a very, very marvelous concept, and I would like you to appreciate it, that it uses a simple definition of energy to explain this particular wonderful concept. Now, before seeing you off, another concept or a term that I would like to introduce is that, well, if I keep on increasing the load and, well, of course, the stress in that aspect, overhead and overhead and overhead and overhead till here, which is the rupture point, then the area under the graph, the whole graph, this would actually correspond to the modulus of toughness. The modulus of toughness would be explained later on in later videos, but this, keep in mind, the whole region corresponds to or is called the modulus of toughness. For next time, thank you so much.